In this result, we are going to prove that a plane curve with constant curvature is either part of plane or it's part of a circle. Okay. So the statement is, let S be a connected surface of which every point is an oblique point. Then S is either part of a plane or part of a sphere. Okay, so we have a connected surface of which every point is an oblique point. Oblique point is a point at which the principal curvatures are the same. Okay, the both principal curvatures are equal to each other. So let us prove this result. So consider the surface S and let us consider a surface patch in the atlas of this surface S with an open set in R2. So let me consider sigma from U to R3, which is a surface patch in the atlas of S with U, a connected open subset of R2. Every point of S is oblique, so both principal curvatures are equal. So let me consider the common value K for principal curvatures of sigma. Okay, both are equal to K. Then we have proved in the earlier class that if K1 is equal to K2, where K1 and K2 are principal curvatures of sigma, then we have F2 is equal to K into F1. Okay. So if you consider the Weingarten matrix, what we have considered in the earlier class, what is that Weingarten matrix? It is the matrix F1 inverse F2 that is given by minus of A, C, B, D. What are these A, C, B, D? They are the scalars which are in the expression of Nu and Nv, where N is the standard unit normal of a surface patch. Okay, so this W is equal to F1 inverse F2. This is the Weingarten matrix, and what is this? According to this, it is minus of ACBD. Correct. So if you consider in this case, I have K both principal curvatures equal. So consider A. What is this? It is minus K 0 0 minus K. Okay. So I have ACBD that is equal to minus F1 inverse F2. So this gives me what is the value of A here? A is equal to minus K, right? C is equal to 0 and B is also equal to 0 and D is equal to minus K. Okay, fine. So again we have by the same result, right? So substituting this in this, what we get, Nu is equal to A sigma U plus B sigma V. B is 0, so and A is minus K, it is minus K sigma U, and Nv that is equal to C is 0, D is minus K, so minus K sigma V. Let us call this as the statement 1 here. Okay, so wherein is the standard unit normal of the surface patch sigma here. So now consider K sigma U, okay, that is equal to minus Nu. Let me consider its derivative with respect to U. So this will be the derivative of minus N sigma U with respect to V. Okay, so this is also equal to minus the derivative of N with respect to V and with respect to U. And again moving back to this here, so Nv with respect to U with minus sign will be K sigma V, the derivative with respect to U. So it is equal to K sigma V, the derivative with respect to U. So from this line what I have, K sigma U derivative with respect to V is equal to K sigma V, the derivative of this with respect to U. Okay. So the derivative of this expression with respect to V, it is K sigma U V plus derivative of K with respect to V sigma U, and similarly here what we have, K sigma U V plus K U sigma V. Okay, so what we have here, K sigma U V, K sigma U V, then we are left with these two, that is Kv sigma U is equal to Ku sigma V. Let me call this as the second statement. Okay, now how is the surface patch here? We are considering the regular surface patch. So sigma is regular, so sigma u and sigma v are linearly independent. So from this statement we can say that Ku and Kv both are equal to 0. So when the derivative of k with respect to u and v both are equal to 0, this curvature must be, this principal curvature must be constant here. Okay, so here we consider two cases depending upon this value of k. Okay, what are those cases? K is constant, so it can be a 0 constant or non-zero constant. Okay, so in the first case, let us consider k is equal to 0. Okay, so when k is equal to 0, statement 1 says that nu is equal to 0, nv is equal to 0, so n must be equal to constant. So this implies that the vector n is constant. Okay, so if you consider the derivative of n sigma with respect to u, okay, n is constant, so it will be directly the derivative of sigma u with n as constant. It's constant, so its derivative will be 0. So it is equal to 0 because n is perpendicular to sigma u. N is a unit vector which is perpendicular to sigma u. Similarly, if you consider n dot sigma with respect to v, then it is n dot sigma v because n is constant. So this is also equal to 0 because n is a unit vector perpendicular to sigma v. So n dot sigma u is equal to 0, n dot sigma v is equal to 0, which in turn n dot sigma with respect to u is 0, n dot sigma with respect to v derivative is 0. So n dot sigma vector must be constant. So n dot sigma is constant. Okay, so when n dot sigma is constant, the image of u, the open set u under sigma will be a part of some plane here. Okay, so this implies that sigma of u is part of the plane which is given by, say, r dot n is equal to constant. Okay, so in this case we are getting s as a part of the plane. Now let us consider the second case where k is a constant but not equal to 0. So in this case consider the statement 1. Okay, so from statement 1 I can write it, integrate it with respect to u. So I have n is equal to minus k sigma plus constant of integration, where a is a constant vector here. Okay, so divide throughout by k. Okay, and take the norm. What I am going to get is norm of sigma minus 1 by ka. Okay, norm of sigma divided by k, take minus side also, so I am left with sigma minus 1 by ka. Norm of this square, I'll take square also, that is equal to, here what I am having, minus 1 divided by kn, so minus 1 by k n. N is a unit vector, so its norm is 1, so square, yeah, this is equal to 1 divided by k square. So what does it imply? It implies that sigma u is part of the sphere. What is the center here? With the center as 1 by k into a, and what is the radius? It is 1 by k, with the radius 1 by k. Okay, so it's part of the sphere with center 1 by k into a and radius 1 divided by k. So what we have considered here, we have considered only a single surface patch here. Okay, so the result holds when S is covered by a single surface patch. So each surface patch in the atlas of S is contained in either a plane or a sphere. But if you consider two overlapping patches, okay, they must be part of the same plane or the same sphere. So the whole of S is contained in a plane or a sphere. So this completes the proof.